Longer battery life is important for mobile phones and other mobile devices. Just as important is the ability to provide a battery runtime specification that is realistic for the user of the mobile device. Validating a battery's stated capacity and energy ratings based on datasheet conditions provides only an estimate of the actual end-use runtime. The most accurate way to determine the expected runtime of a battery is to measure it under actual user conditions. High constant current discharge rates lead to reduced battery capacity. Likewise, high peak pulse discharge currents also yield lower capacity compared to an equivalent constant current discharge having the same average value. The amount of peak pulse discharge that can be tolerated is highly dependent on the battery's internal design. Small differences in dynamic loading conditions for discharging can lead to significant differences in the runtime obtained from the battery. Because of this, you must validate the capacity of a battery under consideration using dynamic loading conditions reflecting the actual end-use conditions. Using the actual mobile device provides the most realistic dynamic loading profile, but has some drawbacks. Not only is it difficult to set up the device for representative operation, but there can be significant variance when doing this on a repeated basis. A more repeatable solution for doing this is to capture the device's dynamic current drain over an appropriate period, and then play it back using a programmable electronic load to discharge the battery. We use the setup depicted here to first power and capture an active mode current drain profile on a GPRS smartphone. The Agilent N6781A source measure unit features full 2-quadrant operation, making it useful as both a high-performance DC source and electronic load. Its biggest benefit, however, comes from being able to digitize its output current profile when sourcing power, and then use the same profile as a dynamic arbitrary waveform input when it is operated as a load. Utilities in the N6705B DC Power Analyzer mainframe and 14585A software further simplify and streamline this task. The captured current profile was a 2 amp peak load with a 0.3 amp average current drain. The captured profile was then played back as a dynamic current load over an extended period to discharge a battery to its low voltage cutoff point. This setup can be used to evaluate multiple batteries with assurance that the results are truly comparable. Here are the display results for a rechargeable lithium-ion battery rated for 1 amp hour and 3.6 watt hour. These capacity and energy values are automatically calculated and displayed over the time period defined by the start and stop markers. Notice that the measured values for battery capacity and energy were slightly less for a pulsed current load than for an equivalent constant current load. As you can see, validating the battery under end-use loading conditions is a key part of determining the realistic runtime of a mobile device. For more information, visit the Agilent website at www.agilent.com/find/N6781.